today's lesson is the arc length. So for example, y is equal to x squared function is here from 1 to 4, and we are finding this arc length, this curvy length. Okay, as a practice, I want you to do this first. We're going to approximate this with a tiny little triangles. So here's what I mean. We'll draw this little triangle like that, right? So this is 1, and this is 1, so this is square root 2, right? Okay, so we'll draw another triangle like that. Something weird happened. So this is 1, and this is 3 now, right? So this is square root 10. Do you know why this side is 3? Okay. And this next triangle, this is 1, and this is 5, eh?
Yes.
So square root 26. And this is 1, and this is 7. Do we all know that 7? 1, 3, 5, 7 pattern. So what we have is square root 50. Somebody punch the calculator and give me a numerical answer. And that is, I'm going to call it, approximately equal to 16 point something. Tell me. Oh, come on. Okay, useless children. So 16.74, 65, and 79 is what it's supposed to be, okay? Now, then we are going to, so if we calculate the realistic lengths using calculus, would that be slightly more than this or slightly less than this? Give me your prediction.
Slightly more. It's gonna be more.
More because?
The concavity.
Right. That's, you're just using that straight line segment, but this thing is curvy, so it's slightly longer path now, isn't it? Yeah, so, but very close to this. That's what we expect. Okay, now I've developed the theory, so I'm going to erase all of this now. So suppose we take tiny infinitesimal. I'm going to draw it below here. So here's a curve, and suppose we take tiny infinitesimal triangle and call this dx and this thing dy, right? Then according to Pythagorean theorem, ds squared will be dx squared plus dy squared, eh? And we can take a square root on both sides, like that. You with me? Okay, then. But we cannot really integrate this form. In order to integrate, what we need is this dx outside, right? So let's factor it out. So this thing becomes 1 plus this thing becomes dy over dx quantity squared. How about that? You get it? That's one format. The other useful form, sometimes we cannot really integrate it like that. I mean, we have drawn the triangle sideways before, right? So we need dy. This is more convenient to integrate. Then this thing becomes this. This is a x as function of y, and this becomes 1. Good. And do you remember parametric equations? X and y are both function of t. Yeah, sometimes we need to do this, and that's actually today's example. So, on today's second example, so then we just factor out dt like that. How about that? Okay, this is chapter 10, so the last one you don't have to worry about it in this chapter, but in polar coordinate we are going to have the theta, polar curve. In that case, it'll be r squared. You don't know where this thing comes from yet. I'll show it to you in chapter 10. It still comes out of this first one. So we only need to this one, only need to know this one, which is just Pythagorean theorem, and the other 4 is just algebra manipulation. Today, for the first example, we're going to use this first one right there, okay? So we do need dy over dx. Okay, so let's go back here. So I will start y is equal to x squared. Okay, and dy over dx is, of course, 2x. And we'll square it while we are at it. So we get 4x squared. Good. And my ds will be square root of 1 plus dy over dx squared. So 1 plus this thingy. Good. That's what we are going to integrate. So my s will be from 0 to 4a. And square root of, somebody punch this into a calculator, make yourself useful. And that gives us, who's ready? 16 point.
818,634.
818,634 is correct. Okay. Now, and then, if you're a good student, you should be wondering, how can we do this by hand, right? Do you wonder? So why don't I show you? Or you don't want to see it? For the recording's sake, I have to do it. Okay, which technique is most useful in this case? Actually, there's only one way that works.
Trig sub?
Trig sub it is. So x is equal to, which one? Which trig? Which trig function? Come on, tell me.
Tangent. It's tangent.
Tangent. Theta. Are we missing one tiny little thing in front of tangent?
Yeah, it should be like 1/2 or something.
1/2 is correct. And rest of you who are wondering why, how is he getting this? My motivation is this, that thingy. What is that? I need to combine this into one term. So let's figure this out. 1 plus, if I square this thing, that becomes 1/4, and that knocks this 4 out. Do you see the motivation? So it turns into this, and that, of course, is secant theta now, isn't it? Do we need an absolute value here?
No,
No, why not?
because it's always positive in the quadrants.
See? This is what we are looking at, right? So, the inverse tangent, just solving for theta, only exists in first quadrant and fourth quadrant, and secant is positive in both of those quadrants. You get it? So we don't need an absolute value, but we do need dx, and dx is the derivative of this, so we have 1/2 and secant squared. Good. Now, let's plug it in and see what we get. So we get this thing is secant, and we have dx, so we need 1/2, 1/2 here, and then secant cube theta d theta. Now we have to change the limits of integration. So according to this thingy or that thingy, when x is equal to 0, theta is equal to 0. That's not a problem. I'm zooming in. Can you guess why I'm zooming in? When x is equal to 4, theta is equal to inverse tangent of 8. It's okay. It's not a special angle, but no problem. It's okay. We know how to do this. Now, how are you gonna? Have I shown you how to integrate secant cube theta before? I think I have. Well, hey, we'll do it again. If it's new to you, then I mean, if you don't remember, it's new to you, right? So we'll do it down here. Okay. Secant cube theta d theta. First, we have to use a little trick. Secant square times secant. You get it? And secant square, of course, is this, according to identity. So far, so good. I'm going to distribute secant and separate this into two separate integrals. So this is tangent squared and secant. How about that? So far so good? Do you guys remember what this first one was? We multiply secant plus tangent, numerator, denominator, it turns out to be this thingy. How many of you want to see this? Okay, nobody. So y'all know how to do it, or you can at least, you think you can figure it out. The second one, what would be the technique to evaluate this integral? Here's a hint. This is a great review now, isn't it? Yeah, integration by part. But which is which? What you have to be careful is you have to know how to integrate whatever you're going to put here. So my suggestion here is this one. Not just secant, not tangent, secant tangent. Because then this b is equal to just secant theta. You know what I'm saying? Then, of course, my u happens to be tangent theta. Then the u, of course, is secant squared. Okay? So, uv plus secant tangent minus the integral. That minus sign comes from this formula of integration by parts. And then these two. Wait. What? We got secant cube theta integral again. Which means we add it to that thingy, right? So what we end up getting here is 2 times integral of secant cube theta is equal to ln secant theta plus tangent theta plus secant theta tangent theta and plus c. How about that? So this means the integral is half of this whole thing. You get it? So divide by 2, and now we go back here and shut it down. So here's a half, and we divide by 2, so we'll have 1/4 of wrong color. And then we'll have ln secant theta plus secant theta plus secant theta tangent theta from 0 to inverse tangent of 8. Oh boy. Okay. 1/4 ln. Let's do 0 first. 0 is nice. If I plug in 0 here, this one dies. This one becomes 1, and ln1 is 0. So don't have to worry about this, and we definitely don't worry about the second one, right? Because tangent 0 is 0. So it's just this, right? In order to do that one, we have to draw a triangle. So here's a coordinate axis. Okay, and I'm gonna draw this triangle. Where did it go? Right here. So this is 1, and this is 8, and that's our theta, isn't it? So is this square root 65, eh? Too much geometry today? Okay. Then so this thingy is inverse tangent of inverse tangent 8 is just 8, right? That one first, so it's prettier. And secant is this thingy over this thingy, right? You know what I'm saying? Wait, somebody got kicked out of the meeting. I'm gonna let him in. Then plus here once again, this is 8, and this one is square root 65. How about that? Wow, that's mother of all integral now, isn't it? Yeah. Okay. Any questions before I move on to the second example? second example is walk in a park compared to that mother of all integral. Circumference of the circle, right? Wow, that's gotta be nice. And of course, we expect 2 pi r to be our answer, right? Okay. I'll throw the coordinate axis here. Like so. So equation of this is, of course, x squared plus y squared is equal to r squared, right? Okay. Now we'll take this tiny little triangle like that and call this ds, this is dx, and this is dy, right? But if I solve it for y, the dy dx itself is pretty bad, right? I don't even want to think about it. So what we have to do is go parametric, okay? So x is equal to r cosine theta, and y is equal to r sine. Why do I say sine and right tangent? I'm going to use t as a parameter instead of theta. How about that? Good. Do you remember this gives you a circle of radius r? It rotates this way. Okay, then I need dx dt, because I'm about to use this formula right here. You see that one right there. You get it? So I need dx dt, which is negative r sine t, and I need dy dt, which is r cosine t. So far so good? So my ds is square root of these two things squared. So I have r squared sine squared t plus r squared cosine squared t dt. Somebody tell me what's under square root?
R?
That is r, right? R squared square root r, right? dt. That's a very nice integrand, isn't it? And we vary that from 0 to 2 pi to distinct traces around 0 to 2 pi and r dt. And this is like one of the nicer integrals out there that just gives you r t, 0 to 2 pi. And of course, that gives you 2 pi r. How about that? Dang, huh? Amazing, huh? Before you think this is the proof of the circumference formula, I don't think it is. I think when I use these two parametric equations, it's already baked into this unit circle. So I really don't think this is a proof. It's a nice exercise. Other things such as the volume of the sphere, these things are all proof, but this one is not. Okay, any questions? Okay, now we're in recording session. So let's look at number 7. Number 7 is, this is an integral function. Interesting, huh? So what is dy over dx? That's just fundamental theorem of calculus now, isn't it? So it just, we lose the integral, derivative and integral cancel each other. So that's just tangent t. Well, tangent x, now you substitute x in here. Good. Now, then we calculate ds. And remember, ds is equal to square root of 1 plus dy over dx, quantity squared, dx. So if I substitute this thingy, it becomes 1 plus tangent square. Somebody tell me what's this inside the square root is?
Secant squared.
That's secant squared, and we take a square root, so that is secant. Do you know what I'm saying? Now, do we need an absolute value here? Whenever you take a square root of something squared, we usually put absolute value. I mean, it has to be a habit, but look at the integrand now, right? I mean, the limits of integration. 0 through pi over 6 is where we are going to integrate this thing over, and secant x, this is first quadrant, so it's positive. Good. Then we can say our s is integral from 0 to pi over 6 of our ds, which is secant. Ooh, that didn't work out. Secant x dx. You get it? Do you remember how to do this one, or do you want me to review this thing one more time? This thing turns out to be ln. This thingy. Who wants to see it? Okay, assuming you all know this, then from 0 to pi over 6. Okay, if you substitute pi over 6, this becomes 2, right? Well, no, not 2. 2 over root 3. So we have 2 over root 3 and plus this is 1 over root 3. And it's a judgment call. Should we simplify this even more? We can. I mean, it's common denominator, split it, but hey, let's just leave it. Good. Any question? Okay, then we'll do number 16. Number 16 is a clever little problem. Okay, first we need dy over dx. So I'm not going to rewrite this over, but we need dy over dx, okay? So we have this expression of y, so let's zoom in a little bit. dy over dx is equal to x squared plus 2x plus 1. So far, so good. Wait, no, I misread it. Okay, there's all of that. So that is -1 power, isn't it? So we will have plus, well, minus, and then x. Let's just do it. I'm gonna get more line. This is the best way to think. Instead of chain rule and all, I'm gonna write down what that y is. My y happens to be, let's just write it like that, 1/3 x cubed plus x squared plus x plus 1/4 common factor, and then x plus 1, -1 power. You get it? That way, we don't have to worry a whole lot, just negative here, so we have 1/4, and then x plus 1. You get it? You get it? Okay then. And we're going to have to add one and do all that stuff, right? You, right? Let's just think about it before, because we have to square it and, oh, no. But do you notice that this is a perfect square? And this is a perfect square. So let me write it like this. Good. Now I'm going to square it, and let's notice what happens. So dy over dx, square. Okay, and I'm not going to really multiply this out. I'll just write it like this. Plus, well, minus 2 times this thingy times this thingy. Do you agree this is 1/2? Too much algebra? Okay, plus 1 over 16, and then x plus 1 to the 4th power. Good. Now we'll compute ds. Okay. Do it over there. Let's do it over here. So ds now is equal to, remember, square root of, I'll just write it, 1 plus dy over dx, quantity squared, eh? Dx. So if I add 1 to this whole thing, that just changes this middle term to positive. So what we have is x plus 1 to the 4th power plus 1/2 plus 1 over 16 x plus 1 to the 4th power dx. Y'all with me? Questions so far? Now, then we have to figure out how are we going to integrate that thing. Do you see it? How many of you see it, this thingy? it simplifies quite a bit. You notice this thing looks remarkably similar to this whole thing, which is something square. This whole thing is a perfect square now, isn't it? Okay, so it's a square root of that whole thingy, right? And notice that this is always positive, right? Besides, we're going to integrate from 0 to 2, but everything is positive sign. These are all positive. So what we get here is, I'm going to use bracket, x plus 1 square plus 1 over 4 times x plus 1 square. You get it? And we don't need an absolute value because this is always positive. You with me? Okay, now we can integrate. Okay, so let's integrate it. Running out of space, I'm going to integrate down here. So our s is equal to from 0 to 2 now of that thingy. X plus 1 square plus, I'm going to write it like this, x plus 1 negative 2 dx. How about that? So that will be here x plus 1 cubed, therefore 1/3, and we don't have to worry about the reverse chain rule. And this thing will be x plus 1, you add 1, so let's change that to negative. Good. And then 0 to 2. And this is the most challenging part. So if I just cheat, I mean, do it in my head, 53 over 6. Any question?
Could you do
Okay
that
then.
for number 7?
Number 7?
Yeah.
Yeah. What about it?
Could you do the graph for it? Because we had to graph it.
Graph this function?
Yeah, I didn't know how to do it.
I don't either. It's an area function, so it's probably, I can try to feel it. So let's try to feel it. Tangent graph goes up like this with a vertical asymptote, right? And we are finding this area function. This is x, right? So we suspect this will be a lot steeper. You know what I'm saying? Do you feel it? So this is
it, but in the answer key, they like made it into y equals the natural log of secant x. And then they graphed that, I think, and I was confused on that.
okay, you can actually evaluate this integral. You know what I'm saying? But I'm saying, why would you want to do such a thing? Okay, I think I have a device. Will it do antiderivative? We'll see. I'm not sure if this thing does antiderivative. Okay, no, that's not what I wanted to do. It does derivative, but it does not do, I don't think it does antiderivative. So we'll resort to our, do you remember this machine that we all possess? Yeah, this one does antiderivative. So let's do it together. So we go here and then clear everything. And then we put math 9, right? And then we can go from 0 to, and we put x here. And then we put tangent x. Yeah, we don't put t, we put x. I think this will work nicely. Ready? And then I'm gonna put it at window size from 0 to, I only need it up to pi over 2, right? So let's just put it to 2. And y scale 1, minimum, yeah. And maximum, let's go way up high, 10. Something like that, because we anticipate this thingy. Integral function takes its time. Wow, it's really slow. Wow, it's really, really, really slow. Huh? What's going on? Is it even working? Hold on. I'm not sure if I'm on radian mode. Ah, this always messes you up. Okay. Yeah, let's try that again. It's gonna give you error. Oh, if I hit that vertical asymptote, it's gonna give me an error message. So I'm gonna change that to pi over 3, right? 1.5. I'm gonna change this to 1.5, okay? Still slow. Why is it not working? Oh, here it comes. I see it. It's rising. Slowly but steadily. And then it's gonna shoot up. Up. Up, 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 up. I have to do this whole thing over because 1.5 is too small for this thing to reach the vertical asymptote. But you see it's that kind of behavior, right? Okay, I'm gonna really, let's see if it goes over to vertical asymptote or gives me an error message. I'm gonna change this to 1 point, what's up pi over 2 numerically? 3.14 divided by, so I'm gonna put 1.7. I think that's the 1.8. Let's put 1.8 and see what happens. Now we have to wait a whole lot again. Oh, by the way, today's lesson is being recorded already during second period, so we can just watch that. Because I'm curious to see this thing through. See, the scale is a little deceiving. This is only up to 1.8, but this is up to 10, so that's why it shows up like this. Because I anticipate vertical asymptote. But I don't know if this machine will evaluate it or says error. You see it's rising quite rapidly now as it reaches that vertical asymptote. See, if you say ln of secant, it's not like you know how to graph that either, right? It's easier to just feel this thingy as an integral function. See, it's almost vertical now. Oh, see, as I thought, it gives me an error message. Okay, I'm gonna run it again after the class is over. We're calculating the length of the asteroid, okay, this whole thing. Now, I mean, one might say, let's just integrate this thing from 0 to 1 and then quadruple it. You know what I'm saying? What's wrong with it? So I'm gonna show you potentially what can go wrong with that idea, okay? They actually give you this? Okay, that's pretty insulting. I'm kind of tempted to start. No, okay, I'm gonna just use this. So if my y is equal to that, let me calculate dy. Oh, green. Why am I having green? Let me start over. So I'm going to find dy over dx. So this thingy. So we have 3 over 2 and 1 minus x to the 2/3 power. And we subtracted 1, so we have 1/2 power. And the chain rule, so we'll have negative 2/3 x to the negative 1/3 power. So far so good? Okay, let's clean this up a little bit. So this is equal to 2/3, 1/3, they cancel, so just have negative and 1 minus x to the 2/3 power. And do I want to, no, I'll just put it like this. What's wrong with it? So far you don't see it, right? So ds is square root of 1 plus this whole thing is square, correct? Okay, so we'll have this thingy 1 plus x to the 2/3 power. So far so good. And then times x to the negative 2/3 here. So far so good, we are squaring it. Yeah, that I forgot 1/3 here. I mean 1/2 there. So squaring it knocks that thing away, and that becomes 2/3 dx. So far with me? Okay. Does this thing simplify? Yes, it does. It simplifies a lot. I'm going to distribute this because there's no power here, so I can just distribute it. So what I have is 1 plus x to the negative. For some reason, I wrote 2/3. This is 1/3. Okay. X to the negative 1/3. And this times this. Am I missing some? It is 2/3. I'm sorry. Because I squared it earlier. Okay. So this thing becomes 2/3. Negative 2/3. And this thing times this thing, they cancel. Right? I'm making so many mistakes. This was minus here. And minus 1. So far so good? Say yes. Okay, and then ones cancel, and then we can take a square root. So we have this nice little expression. I'm gonna have to restart OneNote. It's giving me so much trouble. Okay, we're back. So far so good? Any questions? Now, here's where the problem arises. If you want to integrate, and let's do it from 0 to 1, and then we'll go from here, 8, right? And then, 8, 4, and then of this thingy. So far so good? Now, here's a problem. The problem is when x is equal to 0, this thing is, remember, is in the denominator. Right? You're potentially looking at vertical asymptote. How about that, huh? In this case, by luck, it'll turn out to be okay, but generally, that's a big problem. If you punch this thing into a calculator, it'll give you error message because there's a vertical asymptote of this function at 0. You cannot integrate around vertical asymptote or starting at vertical asymptote. Right, that's chapter 8 stuff. We can actually take a limit, put a here, and then in front, limit a approaching 0 from the positive side. We can do that, but we cannot just substitute 0. This is known as improper integral. And then we can see that right there. You see how vertical it gets up there? Right, that's how I know this will give you a vertical asymptote when you the integrand part. So in order to avoid that, I'm going to cut it halfway right there, right? So instead of 0 here, whatever that point is, I'm going to cut it and then I'm going to multiply it by 8. So in reality, I'm only going to integrate that much. You know what I'm saying? Then we need to know what that point is, right? Right. The way you know is that if I draw that line y is equal to x, then whatever that intersection will be the halfway point, isn't it? So I'm gonna calculate that here on a side. So this equation is x to the 2/3 power plus y to the 2/3 power is equal to 1. And it happens to be a systems of equation between that thingy and this thingy, so I substitute that right there. Okay, then I have 2 times x to the 2/3 power is equal to 1. So far so good? So x is equal to 1/2 to the 3/2 power. You get it? Which is 1/2 root 2. Too much algebra? You get it? Okay, good. So this is 1/2 root 2 at the lower limit. Okay. Continuing, so this will be 8 of x to the 2/3, therefore 3/2 with me. And from 1/2 root 2, yeah, I'll just put 1/2 root 2 to 1. And if you evaluate that, which is challenging part in calculus BC, I'll just put it on the side. Amazingly, you get 6. How about that? Question? Okay, then we'll go to 25. 25 is much of the same idea now. Okay. Let's start. 25, if I just call it y and find dy over dx, don't write this part down, it's not going to work. What is going to happen is x to the negative 2/3, and that therefore 1/3 here, plus 2/3 here, then x to the negative 1/3, right? And remember, ds is equal to square root of 1 plus that thing, dx. These are all vertical asymptotes, and then we are starting from 0. This is a calculator problem, and right off from the beginning, it's going to give you error message. So we can't do it like that. Right, and this is not that symmetrical, so we cannot really apply symmetry. So what we are forced to do here is to find the first function. Whoa, okay, so watch this. I'm going to write this as y is equal to x to the 1/3 power square plus x to the 1/3 power. Do you see this is a quadratic form? So we can complete the square. Have you ever completed the square of something that's hideous? So we'll have x to the 1/3 power plus half of this, which is 1/2 squared, eh? And when I square this thingy up, what we're going to get here is plus 1/4. I'm color coding it just like I'm teaching Algebra 2 class. Okay, you got it? So what we have is y plus 1/4 here. Okay, now I'm solving for this x, right? So I take a square root. So y plus 1/4 to the 1/2 power here is equal to x to the 1/3 power plus 1/2. So x is going to be, I'm gonna move over, so we have y plus 1/4. Huh. This one note is really acting up. Of the 1/2 power minus 1/2 the quantity cubed. Good. Say yes. Who's lost? Too much algebra? Okay, now we have to take a derivative here. So dy over dx now is equal to, we have 3, and then y plus 1/4 to the 1/2 power plus minus 1/2 squared. And then chain rule that inside thingy, so I will have 1/2 and then y plus 1/4 and then 1/4. So far so good. Then you might say, well, doesn't that create, that's on the denominator too, so doesn't that create the vertical asymptote too, or in this case horizontal, or whatever, the asymptote. That one is okay because the location of that asymptote is y is equal to -1/4. You get it? So we're okay. Now, then our ds is a square root of, gigantic square root of 1 plus this whole thing is square. I'm going to put it as 9, that thing is square of y plus 1/4 and then 1/2 power and this thing in the denominator, which is 4, and then this one gets nicer.
It should be dx over dy.
Dx, yeah, that's correct. Nice catch. Dx over dy. Like that. Good. Now we have to integrate. So my s is equal to, now limits of integration, this is not 0 to 2 because x varies from 0 to 2. I kind of stopped there in the Dropbox note. If I plug in 0 here, I get 0, right? If I plug in 2 to the 1/3 powers, oh my God, what is that thing? Can somebody compute that with a calculator and tell me what that is? Upper limit? I'll just write it. We can do that. 2 to the 1/3 power plus 2 to the 2/3 power, whatever that is. That's our limits of integration now, isn't it? You realize that? Okay, then this is too much gigantic mess, so I'm going to just do copy and paste. Then all of this. What's wrong with this? Resize it a little bit. And all of that goes in here. Okay, and that becomes, punching the calculator, gives you 3.6142.